I'm sure lots of people in the audience have got questions, but while you're preparing your question, there's a question from Martin from Mayfair, who'd like to know, how did the LIGO detector know that it was two neutron stars rather than a black hole colliding, and have they detected any other things colliding that have sent out ripples?
Yeah, so I should say I'm not an expert in this stuff at all.
Well, that's what happens when you're
I think, so what they look for, I mean, just to say a bit more about LIGO, so I met the head of the LIGO lab at Livingston, and what he said to me is that the distances they're measuring are smaller than the size of it. They're measuring, basically these laser beams, what they do is they measure shifts in the length of the arms caused by these gravitational waves. And they're measuring shifts that are smaller than a proton. So this is unbelievably, fantastically tiny distances. I think he described it as like the private space enjoyed by two quarks. So the fact these instruments work at all is amazing. And actually, when I was there, I walked in, he showed me around the control room. I went into the control room, and just as we walked in, everyone got up and was looking very excited, and they said, well, we just lost lock. What that meant was that there'd been an earthquake in Indonesia, and the seismic waves from that earthquake had sent all their optics out of alignment. So they've got to correct for, or balance against all these other vibrations in the earth, and in order to detect these incredibly fine shifts, which is amazing. So, but what they essentially do is they look at this signal they get out of the instrument and they search for particular waveforms. I think they basically have templates. So they a black hole collision has a certain ripple shape. Neutron stars have a different shape. So I think it was basically from the shape of these waveforms. And the thing that was then very convincing is when they've discovered when they found this signal, they sent out basically an embargoed alert to a load of optical observatories that they had connections with. And they then looked at the sky and they saw an electromagnetic glow. So they saw light effectively created. Because when black holes collide, they don't create light. They just go boom, and they create lots of gravitational waves. But when neutron stars are incredibly hard, dense objects, when they smash into each other, they get a lot of light, a lot of heat. And that's what they picked up. So I think that's why they're pretty sure that is indeed what they saw.
Oh, fantastic. Is anyone here? Gentleman at the back? So I'll just repeat that for anyone watching at home. The question was about, were the laws of nature the same all the way right back to the start of the Big Bang?
It sort of depends a bit what you mean by a law of nature. But yes, as far as we know, the laws of nature haven't changed. So the laws of nature tell us, if I have a particle and another particle, how do they interact? How do they accelerate? How do they move? What are the forces that are exerted on them? So if you could have built a motor in the fireball of the Big Bang, it would have operated on the same principles as now, although you wouldn't have been able to because you'd been vaporized. But what does change as you go back, particularly at this moment I described where the Higgs field switched on, that moment rearranged all the ingredients of the universe. So it rearranged the properties of all the particles. So actually, the fundamental forces that exist in the universe today had a completely different form before this moment. And the Higgs field basically allowed them to take on their current form. In fact, even the matter particles that we know, there were different numbers of them because basically the particles that we are made of are actually mixtures of particles that have right and left-handed spin. And so the basic ingredients would look very different. The laws that govern how they behave would be the same, but the particular particles would have not looked the same.
Does anyone else like to ask Harry a question? Yes, please.
Yes, I'm not sure how this fits in with the apple pie, but the gravity, the graviton is something that's missing from the standard table. And this is what the gravity waves are looking for, but so far it hasn't been discovered.
So again, that's a question about the graviton and where that fits into the standard model.
Yeah, so gravitons are the analog of, say, the photon. So you have electromagnetic field, a photon is the ripple in electromagnetic field, graviton is the ripple in space-time. So in principle, a gravitational wave is made up of lots and lots of gravitons, but the gravitons are so fantastically weak that we haven't yet found a way of detecting them individually. I didn't really talk about this quantum gravity, which I guess, for a long time has been one of the holy grails of physics. So this is a theory that would combine quantum mechanics, the language that we use to describe particle physics, with gravitation, which we currently describe using Einstein's general theory of relativity. And one of the reasons that a quantum gravity theory would be exciting is that it would allow us to study, well, at least theoretically study the moment of the Big Bang, because at the moment of the Big Bang, the universe is so small and dense that quantum gravitational effects would have been very important. The reason I don't really get into it is because I'm an experimentalist, and so far at least, there aren't any prospects of measuring, at least not these high-energy quantum gravitational effects. Now, I believe there are some proposals to try to detect individual gravitons using, in fact, I think possibly even using LIGO. Now, I don't know if there's any experts on gravitational waves in the room, there might be, but I think that is right. So there may be ways of potentially detecting the imprint of low-energy quantum gravity. But in terms of the sort of high-energy quantum gravity, which is the quantum gravity that would have dominated the moment of the Big Bang, at the moment we have no way of probing that kind of physics, and it's kind of even hard to imagine how we ever will. And the reason for that is basically that the best way we found of studying the physical stuff and the ingredients of our universe is by colliding things with colliders. If you want to probe the energy scales of quantum gravity, with current technology, you'd need a particle accelerator the size of the Milky Way. So you might call it the impossibly large hadron collider. In fact, I have a little satirical bit in the book where I imagine the far distant future where we built such a thing. But that's not going to get funded anytime soon. We're going to have to come up with some kind of pan-galactic collaboration if we're going to do that.
I think there's another question somewhere in the center. Yep, person there.
It was around the value, the 246 value for the Higgs field, and what is your speculation perhaps at this stage, with that being in regards to the multiverse theory?
Well, I wouldn't presume to make any speculations because it's way beyond my pay grade. But I mean, the basic, there are a few different ideas, which I didn't get into for reasons of time. But the most popular solution to this problem is something called supersymmetry, which is a theory the idea has been around for some decades now. And one of the key reason that supersymmetry, physicists thought that they might see supersymmetry at the LHC, is that if supersymmetry is right, and what supersymmetry basically says is that there's a new symmetry in nature which relates force particles to matter particles. So what technically are known as fermions and bosons. So matter particles are all fermions. They all have spin 1/2. So particles behave like they have a little, like they're spinning effectively. And then there are the force particles, which are bosons, which have either spin 1 or spin 0 in the case of the Higgs. And in supersymmetry, every particle in the standard model gets a superversion where it's exactly the same, but it has, if it's a fermion, it becomes a boson, and if it's a boson, it becomes a fermion. And they're called sparticles. They all have very silly names like selectrons. My least favorite, I think, is the strange squark, which tends to make you spit in your person you're talking to's eye. Anyway, the reason this is a promising idea, one of the main reasons it's promising, is that if supersymmetry is right, it explains why the Higgs field has this particular value, for technical reasons I won't get into. So that's one solution. Another solution was maybe there's extra dimensions of space, and that's something that people are also looking for. If that's right, then you can make micro black holes at the LHC. Again, we haven't seen that. So the most promising ideas, at least in their simplest forms that have been looked for at the LHC, haven't been found. Now, that isn't to say they won't still be found. The LHC is going to run for another 15 years, more or less, and my colleagues at CMS are still searching hard for these things. They may well show up. It may just be that they're a bit more difficult to see. They're a less vanilla version of what we were expecting, and they're hiding in the data. So maybe we will see them. But as you mentioned, if we don't find a solution to this problem, another ready-made solution is the multiverse, which is the idea that there are multiple universes, and the basic argument would be if there are huge numbers of different universes, they all have different values of the Higgs field, and we live in the one we do because it's the only one of the only very small number where the conditions are right for life. The problem I have with the idea of the multiverse is that it's untestable, because if there are other universes, well, by definition, the universe is the thing we can observe, so any other universes we cannot observe. So the multiverse, in a way, is a bit like God, right? You can't disprove the existence of God. So God could unzip the sky one day and say, hello. And the same way the multiverse could show up if another universe, say, pushed into ours and changed the way that things were arranged on the sky. But if that doesn't happen, that doesn't mean that the multiverse doesn't exist. So it's not testable. And the other problem is it's sort of an all-purpose solution to any problem you can think of. So, you know, it explains why the Higgs field has its value. Maybe it also explains why there's matter in the universe. Maybe just by random chance in our universe, there just happen to be a bit more matter. But you could take this to ridiculous levels. You could say, well, you know, why did my mum and dad, for example, meet at a British Telecom training conference in 1974? Well, it was the multiverse. Because if it wasn't for that, I wouldn't be here. So that's sort of an anthropic argument taken to the extreme. So yeah, it's a possibility, and it could be right, of course. It could be that there are other universes. And the history of science has sort of showed us that every time we've understood more about the universe, we've realized that our place is less and less special. So the idea that our universe is one of many sort of makes sense philosophically, but we'll never know. So we would, certainly, you're not really supposed to have prejudices as an experimentalist, I guess, but I'd much prefer that we found a solution to the problem rather than just going, oh, it's a multiverse.
And just to clarify, you said under supersymmetry, would that also apply to antimatter particles? Would they also have their supersymmetric?
Yes, there would be anti-strange squarks, anti-sparticles, yeah.
That seems far too complicated. So there's a question online from Roger, who is asking about something that wasn't, I don't think, on your standard model, which are neutrinos.
Oh, yeah.
It sounded like you were slightly trepidatious about this question. Yeah. So Roger was just asking, do neutrinos acquire mass via Higgs or not? And if so...
We don't know yet, is the answer. So they might do. Neutrinos are weird because neutrinos have really, really tiny masses. Their masses are millions of times smaller, I think, than the electron even, for example, or at least hundreds of thousands of times smaller. Although we haven't measured their masses directly yet. So they could get their mass from the Higgs field, but the kind of weird question is, well, why are they so light compared to all the other particles? Another possibility is they get their mass from something called the Majorana mechanism, which is very technical. But for that to be right, basically what that means is that neutrinos and antineutrinos are the same thing, that there is actually, they're the same particle, basically. And if that's true, they get their mass from a different sort of process. So they might get it from the Higgs field, but they might get it from a different kind of mechanism.
Fantastic, thank you. Is there a question at the front?
Can you explain why there seems to be more matter than antimatter in the universe?
No.
So the question was about, is there...
We'd love to be able to
more
tell
matter
you.
than
But that's what me and my colleagues, and my boss Val, who's here, one of the questions that we work on at LHCb is that question. And so one of the things that we do, for example, one of my things my colleagues do is they, again, looking at these beauty particles. Another reason they're interesting is because beauty particles, you never actually see a beauty quark on its own. It binds up with another quark to make something called a meson. And these mesons, these beauty mesons, they have this strange property, which is they can oscillate between their matter and antimatter versions. So you can do various measurements where you see how much time do they spend as matter, how much time do they spend as antimatter, roughly speaking. And if you see a big difference, that can be evidence of a new kind of matter-antimatter symmetry breaking that could help answer this question. So that's one of the other ways we might try to get, answers to this problem. But we don't know. No, we don't know yet.
So a few people online, including a 12-year-old, thanks for that question, says, could we ever work out if anything happened before the Big Bang, or what happened before the Big Bang? Or is it basically we've wound the clock back and it just comes to this point and there would never be... It's sort of a meaningless question because there is no time or universe before that. So how would we ever know? Do you think it would ever be possible to know?
So, well, I spoke to actually a colleague at Cambridge who's a theoretical physicist who's spoken here in this lecture theatre. I think he's one of the most watched videos, I think, which is David Tong. Yeah, and he's worked on sort of ideas a bit like this in the past, I think. But this process of inflation basically suggests that we probably can't. And the reason is you have this incredibly rapid expansion. So as I said in the talk, any information from an earlier period gets carried out of view. We'll never be able to access it. So if inflation in its sort of understood, its sort of accepted form is right, then we probably won't ever get any information from before that time. Now, there are some qualifiers. I think Roger Penrose, I remember going to a talk when I was a student by Roger Penrose, who won the Nobel Prize last year, and he was working on an idea that you might see shapes in the cosmic microwave background, so in this radiation left over from the Big Bang. I think he was looking for sort of circular patterns on the sky that in his particular model would be produced by the sort of echo of an earlier universe from before the Big Bang. And they looked for them and didn't find them. So, I mean, there are people who do think about these things seriously and come up with suggested observations that you might make. But at least I think in the sort of the accepted cosmological model, inflation is basically like a barrier, and that says, that's your lot. That's as far as you can go. which is possibly a little bit frustrating. But on the other hand, it does mean that we've got something to aim for.
But there does seem to be these hard limits elsewhere in physics where, you can never know the momentum and the mass of a particle. You know what I mean? Like there are written into the laws of nature and into physics these kind of barriers that mean you can never know X because of the way the universe is set up. It wouldn't be unusual, I guess.
And that's one of the things I discuss in the very final chapter is, the limits of what's knowable. And there's no reason, actually, with a lot of these questions, the universe doesn't have to be nice to us. It could just leave us with these mysteries and never allow us to know the answers because of the particular way that the laws of physics are configured. But we're still plugging away anyway and see if we can get answers.
Fantastic. We've got about 10 minutes left. Any more questions? Person in the front?
You mentioned that the Higgs field was switched on in a few moments after the Big Bang. What other fields switched on at different points? And if they were always on, what was special about the Higgs field for its switching on at that particular moment?
So again, for those at home, it's all about when the Higgs field was switched on and were other fields switched on and off.
Yeah. So, well, in the fields that we know about in the universe today, as I said, they all have a value of 0. Well, not quite 0, because because of quantum mechanics, you can never know that something has an energy of 0. So there's this quantum fluctuations that go on. But the Higgs field has a non-zero value, and it's the only field like it that we know that has this property. So the other fields, they are affected by the Higgs field. So, for example, the masses of the particles that are produced in those fields change when the Higgs field comes on. But I think otherwise, those fields sort of haven't changed. There wasn't a phase transition in quite the same way. Now, there may be other fields that we don't yet know about that went through other transitions earlier in the history of the universe. But the Higgs field is quite special in that way. It's the only one, as far as we know, that actually went through this change where it went from 0 and acquired its current value. And the big question is, why did it do that? And why didn't it end up somewhere completely different? Why did it end up in this particular Goldilocks place, which means we can exist?
Fantastic. So many questions. Fun.
How are you that they will actually find evidence for supersymmetry?
Yeah. Well, I don't know if I have a strong view about that per se, but I mean, I know that, something that's quite... So at Cambridge, there's a group of experimentalists and theorists who meet every week on a Wednesday morning, which for many years was called the Supersymmetry Working Group. So they were a group of theorists and experimentalists, and they came up with ideas for things you could look for at the LHC. And I think it was in 2019, they quietly rebranded themselves as the Phenomenology Working Group. So I think that maybe gives you a hint of the relative levels of optimism. So a lot of people who spent a long time working on supersymmetry, they haven't given up on it necessarily, but they're saying, well, we didn't see it in the first few years of the LHC. We're probably not going to see it immediately. It may come, as I said, in a decade or something from now when we have a lot more data. But for now, at least, it's probably not where the action is. Actually what this group now discuss a lot of the time are these anomalies that I talked about that are seen by LHCb and this experiment at Fermilab. So those are the sort of promising areas. Now, those anomalies could be connected to supersymmetry some way, but it's still too early to say.
Another theory that people are mentioning in the chat, actually, is string theory. You haven't mentioned the word string at all in this entire presentation. Do you think it's now sort of old news and nobody cares about it, or is it theory and you're an experimentalist and show me the evidence and then you'll talk about it?
A couple of reasons I didn't mention it. One is I don't understand it, and lots of people have given talks about string theory. It's discussed endlessly, and it's a really. And I spoke to string theorists when I was researching the book, and it's definitely it's a really fruitful area of mathematical exploration. Lots of useful stuff, not just to do with quantum gravity and theories of everything, but understanding quark gluon plasmas, like the one I talked about that they produce at this experiment in New York. So they're using it for various different things. They're making discoveries in pure mathematics using string theory, but at least so far, string theory has yet to make contact with the experimental world, and it's quite hard for the foreseeable future to see how it will.
Set up a meeting every Wednesday morning? No?
Well, yeah. I mean, there is. I mean, some people. One person I spoke to, who I won't name, he was a string theorist, but he gets very frustrated because he says he thinks a lot of his colleagues have very little interest in connecting with experiment. And he actually works in string phenomenology, so trying to think of things you might look at, particularly relating to the early universe, where you might get evidence of string theory. But basically, yeah, I think it's interesting, it's really important, but it's not yet making experimental predictions, and therefore, that's why I didn't go into it, really.
Yeah, it seems to be a recurring theme, actually. Multiverse, string theory, anything you can't test, you're not so interested in.
Yeah.
So just time for a few more questions. Hank?
Two questions. You have mentioned, obviously, dark energy and dark matter,
Yeah.
very much outside your field. But do you think, obviously, that the implications sort of implications on what you do.
Mm.
The other one is obviously there's a relationship between energy and matter for us in Einstein. Do you think that's going to be the same for dark energy and dark matter, or no idea? I mean, are they likely to be related in the same way that energy and matter are?
Mhm. So for those at home, there's a question about dark energy and dark matter and whether they'd have similar properties. And what was the first question? I forgot now. About the existence of...
Affecting his future work.
Yeah, so if they were discovered,
Yeah.
will they mess up all the results from the LHC?
Yeah. Well, just for reference, this is a slide I didn't show you. This is the sort of the next pie chart in the series of what the universe is made from. So we have 5% atoms. That's all the stuff I've been talking about, the stuff in the apple pie. And then there's 95% dark stuff, dark energy and dark matter, which are really just words to cover our ignorance. They basically mean, if we were to discover what dark matter was, and that's one of the big goals of the LHC. A lot of my colleagues at the LHC were searching for dark matter particles, and there are also experiments going on underground where people are looking for dark matter. If it was discovered, it would open up a new set of ingredients of our universe, and it could well be connected to these other questions. It's not guaranteed that that's true, but if you learn something fundamental about the world, then that's going to be exciting, and it could well open up a whole load of other issues that you were trying to solve. So they could be connected. And an example of this is supersymmetry. So supersymmetry actually explained the reason supersymmetry was so popular, was so popular, still is popular for some people. It solves this problem with the Higgs field. It explained what dark matter was, and it also in some cases explained why there's more matter in the universe than antimatter. So they could be connected, or they might not be connected. But if we were to learn something about them, that would be hugely important. To your question about whether the equivalence of matter and energy would still be true for dark matter, well, yes, because dark matter, we would imagine, is just another quantum field with a particle associated with it. It would just obey the same laws of physics. And the equivalence of matter and energy is a sort of a law, as opposed to the particular particles that happen to exist. So yes, the same physics would apply.
Excellent. So as we sort of draw towards the end of the event, there's a question for somebody's 4-year-old here, who says, given how much we still don't know, what area of science would you recommend a father gets his 4-year-old daughter to focus on as his retirement plan? I mean,
as his retirement plan?
I mean, learn to code is generally quite good advice.
I mean, none of this, because you're not going to make any money. I did have an idea, actually, for setting up an alternative therapy center where you use neutrinos to treat people.
Nice.
So you can kind of say you're getting very expensive neutrinos from CERN. It's going to cure all your ailments, a bit like homeopathy or something. But short of scamming people out of their money, I don't know. I mean, in terms of the things that I think are really interesting areas at the moment, obviously I think the stuff I work on is really interesting, and these anomalies are really exciting. Gravitational waves, I think, are really exciting as well. That, you know, the thing that's great about gravitational waves is, and actually at Cambridge, led by Val Gibson, who's my boss, they're working on a project to build a gravitational wave detector called AEON. This is a whole new type of astronomy. So it's a bit like when Galileo first used the telescope to look at the heavens. You suddenly discover a whole load of new things very, very quickly. So gravitational waves is like that, and it could be as revolutionary. It's a new way of looking at the universe, and we're already discovering new things that we didn't know about black holes and neutron stars, as I discussed. So I think that would be definitely an area that you should think about. Yeah, and in terms of making money, I have no idea. I wish I was any good at that.
And just to say that normally when people ask these kind of questions about what should you study at university or what should you learn, I always just say maths. The more maths you know, the rest of your life, it just gives you tools that you can then apply to absolutely anything you want to do, going into business, being a particle physicist. I just think the more A-level maths or GCSE maths and whatever you can learn early on, I think that always puts you in good stead to do whatever kind of science or not science you want to do. I don't know, were you a maths geek at school, or was it really physics for you that you really went into?
I hesitate to say this, but I was never very good at maths. Okay, when I say I wasn't very good at maths, I was pretty good at maths compared to most people, but compared to people who are actually good at maths, I wasn't very good at maths.
That's like me.
So I think the thing with maths is no one ever explained to me what maths was. So I remember being told how to solve second-order differential equation at school, and you're given this recipe, basically, for how you do it. And I was like, okay, but so what? Like, why? Why is this the recipe? And no one ever explained that maths is essentially a set of rules, and then you play this logical game, a bit like kind of a crossword or a Sudoku or something, and you figure out the consequences of those rules. If someone had told me that, I think I might have liked maths more, but I didn't realize that until way too late.
But yeah, it's sad to say, being no good at maths is what sort of stalled me at about first year physics, and then I couldn't get any further. So I
think Einstein said he was bad at maths as well. So if that gives you any comfort.
So we've probably got time for like one more question. So if you want to ask it, make it good, person there.
Artificial intelligence seems to make a lot of discoveries at the moment. Is it being used in your field at all?
So it's a question again about using AI to make discoveries. I assume with the buckets of data that come out of the LHC, nobody can look at it all. So you must have to use some kind of machine learning to get to grips with stuff.
Yeah, absolutely. It's a really important part of what we do. So to give you a sense of the data volumes that are created, the LHC collides protons inside each of the experiments 40 million times a second. And in each of those collisions, there may actually be 40 or 50 or 100 collisions. So you get billions of collisions every second. That happens 24 hours a day, 7 days a week for about 9 months of the year. So you're talking of tens of petabytes or more of data every year. So, and so what you're generally looking for, you're looking for some tiny signal buried in that data set. And the sort of, when we started out, the sort of simple thing you would do is you set a set of what are called cuts, but they're basic requirements. You say, this particle has to have a momentum bigger than this, an energy bigger than this, has to be going in that direction. And then you use those sort of requirements to filter the stuff you're interested in. But you can do much better with machine learning. So I use relatively simple kinds of machine learning in the data analysis that I do in order to extract. I work on very, very rare decays of these beauty quarks. And so we're looking for events that only happen sometimes 1 in a billion times or around that order. So to try to get those tiny little grains of gold dust out of this huge swamp, we use a lot of machine learning. But it's going to be an even more important area in the future. So what's currently happening at LHCb and will soon be happening at the other LHC experiments is the experiments are being upgraded to allow them to record data at an even higher rate. And the reason for this is after a few years of running, you get this law of diminishing returns where each year of data is a smaller and smaller proportion of what you've already got. So to discover new stuff, you then have to go to an order of magnitude faster data collection rate. And that has all kinds of challenges for computing, for storage, processing. And so when we restart next year, hopefully, increasingly there'll be machine learning algorithms running live on the experiments. They'll be running in what are called the triggers, which are these very rapid algorithms that look at each event one by as they come in and decide whether to keep them or not, because we can't store that volume of data. So yeah, basically the short answer is very, very important.
But also it's another really good example of how CERN and the LHC are just at the cutting edge of computing. That I was using a thing called the web earlier, and and so that's just one example of the sort of the computing power and knowledge and technology that's kind of come out of the work that you do at CERN, I think. Yeah. Fantastic. Well, I think I'm probably going to have to draw this event to a close as the time is somewhat against us. But I just want to say a big thank you all for coming. It's been fantastic to be in front of a live audience rather than just in my living room staring at my laptop. So thank you so much. Obviously, everyone here has already become a member of the Royal Institution, so I don't need to advertise it to you. But if anyone's watching at home, just a reminder that anyone in the world is welcome to become a member of the Royal Institution. There's no nomination. There's no qualification. They let me become a member, so, it's open to absolutely everyone, and you just need to like science and want to support what we do. So for those of you who are watching online, please do fill in the survey afterwards and let us know what you thought. Before we go, I'd like to show the books again.
Yes.
And I'm happy to confirm, by the way, I did ask Harry earlier, there is actually a recipe for apple pie in the back of it.
Just in case
so you won't be missold. If you only bought it for the apple pie recipe, there is one in there.
It does start with quarks and things, but it gets to pastry eventually, so it is in there. Yeah, so I hope you enjoyed the talk. Do buy the book if you did enjoy. This is the UK version, which is rather lovely. And there's also, if you're in North America, this is the North American version. You can't buy it here, though, unfortunately. But I think I'm going to be, hopefully, signing some copies outside.
Yeah, I hope so. I mean,
if the bookshop's turned up.
Let's be full disclosure here. I checked and I did email Blackwell to come and sell books. They hadn't turned up when I started this event, so who knows if they're going to be outside this door now? They might be. We'll see. It'll be a surprise for me as it is for you. But in the meantime, thank you so much for joining us. For those of you online, of course, you can click some of the links that we've been posting in the chat to get a copy of Harry's book. Oh, just before we go, I believe you have a website or you're on Twitter if people want to say hello and send you messages.
My website's harrycliff.co.uk. You can find out what I've been up to. And also I'm on Twitter at harryvcliff. So yeah, follow me if you've enjoyed this.
Fantastic. Well, thank you so much for an absolutely wonderful talk. And best of luck with the book.